Welcome to this pre-recording of the first half of lecture 15, scheduled for the beginning of the 6th week of our 8-week summer course on computer algorithms. So we have considered graph algorithms, greedy algorithms, divide and conquer, dynamic programming. This week we start a new chapter on iterative algorithms, and the focus will be mainly on the Ford-Fulkerson algorithm and its applications. So we are looking at weighted directed graphs, and we see those graphs as networks. So we have a source and a sink. So here is one of the simplest non-trivial examples that we will be using in our derivation and our design, if you like, of the Ford-Fulkerson algorithm. So every edge has a direction. It goes from a source S to a sink or a destination or a target. Every edge has a weight, and we call this the capacity. In previous lectures, we called it the cost. Now it is a capacity. All the nodes other than the source or the sink are the internal nodes. So here you see an example of a graph of 4 vertices and 5 edges. Typically, what we study in computer science are algorithms to process information. Here, a good application is to study the flow of information and to look at our graph as a communication network. So what do we mean when we say flow? Well, flow is a function on the edges. So we have a capacity on every edge, but we will impose a flow on the edges. And you can think also as flow as some fluids and the edges as pipes, if you are more a hands-on plumber type of person. So that's the definition of a flow. It's a function on the edges, and the capacities are positive. Also, the flow is positive. So there are two constraints on a flow. For it to be a flow, we cannot exceed the capacity. So if the edge has a capacity of 3, then the flow on that edge cannot be more than 3. The other constraint is that what comes in has to go out. So there is this conservation. So in going from the sink to the source, we have internal nodes and they do not leak. So we don't put more flow than the capacity. Our pipes, if you don't, they don't stretch, and there are no leaks in the plumber terminology. Okay, so then we want to optimize always something in this course. So what we want to optimize, what we want to maximize is actually the value of the flow. So on every node, we have the outgoing and the ingoing flow. So the edges are directed. We have incoming edges and outgoing edges. So the value of the flow is typically by the conservation laws, whether we talk about the incoming or the outgoing, it's actually just the same. So in some sense, I should emphasize this. What we have is we have that by the conservation law, so it is now very precisely written down. So the incoming, what comes in a vertex is the same as what goes out. We can also define this for a set of nodes, or essentially all a set of edges. Okay, now what is our problem? We have the maximum flow problem given on input a weighted directed graph with single source, single sink, and every edge has a capacity. Then we want to find an assignment of values to the edges. So that's another way of looking at this function f, where the value is as large as possible over all possible flows. Again, there's always, for the small graphs, there is always the brutal force method that you try all possible numbers. So in the first half, we will introduce the algorithm. In the second half, we will discuss properties. If we compute the maximal flow, we will actually also figure out where the bottlenecks are. And if you want to increase the capacity of your network, it will actually indicate on which edges you have to increase your capacity. Okay, so it's time for some reflection, for some exercises. Looking at examples, we only see one example of an input. Is the solution to this maximal flow problem unique? And this is not a yes or no answer. You should give examples where indeed it is unique. Think about when all the capacities are different numbers. Then if you want to maximize something, you essentially grab some of the edges and you look in one path what is actually the maximal flow that can go through this. If the numbers are sufficiently different from each other, this will be unique. Now, if on the other hand, in the other extreme, if you have capacities that are all one, then you should come up with an example where there are many assignments of flow to the edges that have the same maximum flow. So first of all, what does maximum flow uniqueness mean? It means that you have a unique selection of the edges where you impose the flow that gives you the maximum. The maximum is a number, and different assignments can give the same flow, the same maximum flow. And this happens when the capacities have all the same numbers. It doesn't happen if the numbers are all different, sufficiently different. Okay, so one source, one sink. Well, if you live in a one-bedroom apartment, even that may not be true. You will have multiple sources, I hope, for liquid coming in and multiple sinks. But everything can be reduced to one source and one sink. In some sense, that is true. You have only one water company that gives you the main source for your water. So here for this exercise, figure out write an example with two sources and two sinks. Figure out some capacities. You can probably recycle some of the previous exercise and explain how you can actually transform the network. If you have multiple faucets, they all actually link up to the main entrance where the water enters your building. So you have to refer to that. And all the sinks, they can be connected to one sewer system. So that's the plumber explanation to this answer. So let's start thinking now about an algorithm. So we will gradually describe the Ford-Fulkerson algorithm. Okay, so we have in the first half this very simple, non-trivial, um, simplest non-trivial example. In the second half, I will start with a worked example. So we have at the left a network, and we look at a path from the source to the sink, and you can see we are still a little bit in the mood of greedy algorithms. You have two directions going from the source to the sink. Let's take the direction that has the maximum flow, that passes from S to U, from U to V, and then from V to the sink. So that means that we can impose a flow of 20. Um, so finding a path from source to sink from two nodes is a problem that we studied very early on in the course and which you may still remember from data structures. Okay, so this is a lecture on iterative methods. So as you may suspect, we are not done yet. So the maximum flow is actually larger than 20. Um, how are we going to compute this? Well, we're going to redirect some of the flow. Um, so we see that there is another path here to leading into the sink of a path, an edge that has capacity 10. We can interpret that we are going to reroute 10 units of flow from U to V. So we imagine here that 10 units of flow, of the existing flow that we have now of 20 in this network, we are going to redistribute 10 units. So that means that there is here a fictitious edge that runs in the opposite direction, and that allows us to redistribute 10 units of flow from V to U to the sink. And in the dashed arrows here, you can see that there is actually room for an additional 10 units. And the dashed arrows are what we will call an augmenting path. Okay, so how is this path defined? Well, we will define the residual graph. The residual graph has the same vertices, but then you have forward and backward edges. You have forward edges with diminished capacity, where you subtract the flow, the existing flow, from the capacity. And we have backward edges that will allow us to redirect flow. If there is flow on an edge, the residual graph will um, have a backward edge. Note that how large is that residual graph? Well, it's of the same size as the original graph. So at most, we are going to double the number of edges. So the size of the graph is of the same order, same vertices, potentially doubling the number of edges. Here is an example of a residual graph. So at the left, we see in red the flow. We have a flow of 20 from source to vertex U, and 20 is also the capacity. So there is no forward edge anymore. So we are not going to draw an edge with zero capacity. An edge with zero capacity is a non-existing edge. we simply have a backward edge here. We do have a forward and a backward edge from U to V. So we have the original edge U to V with capacity 30. There's only a flow of 20 on this, so we have a backward edge, so we add actually an edge, and we decrease the capacity of the edge from U to V, subtracting the existing flow of 20. And then we also flip the edge from V to the sink. Okay, so the solid edges mark the residual graph. Now, if we are looking for a path from source to sink, then you see that we are kind of forced to go from the source to V, and then we cannot go from V directly to the sink. We have to go via U to the sink. So the dashed arrows define another path that still has capacity 10, or actually we will call it the bottleneck. So of the existing flow 20, we can increase this by 10. So this is the second step in the algorithm. Okay, let me formally define what is called residual capacity. So in a way, the residual graph, is not exactly constructed. What is constructed are the updated capacities. And we could also see this as we have multiple numbers that can be assigned to the same edge, that we have two numbers, depending whether we are still looking forward or whether we're still looking backwards. So here is the formal definition. So if we have a forward edge, we subtract from the capacity the flow on that edge. And then we have the backward edge, the corresponding backward edge that has the flow. So in the example, if we have a capacity 16 and on that edge there is a flow of 11, we can increase up to 5. So that is what the first number says. The second number says that we allow for the redirection of flow. We allow for the return of 11 units to redirect the flow. Then the bottleneck. So here is again the definition of the residual capacity. The residual capacity is assigning numbers to the edges in the residual graph. We look at then if there is a path, and the bottleneck on a path from source to sink is the minimum of all the residual capacities. And if that path exists, the bottleneck will be positive, and we will have an augmenting path. And then we can increase the flow by the bottleneck, by the value of the bottleneck. So two definitions on this slide. Well, actually three. So you see the residual capacity still here for an existing flow. If the residual graph permits a path from source to sink, no repeat nodes, then the bottleneck will indicate by how much you can increase the flow on that path. And since we are increasing the flow on the network, we call that path an augmenting path. So the algorithm will repeatedly construct augmenting paths until there is no more augmenting path that can be found. And that will then lead to the termination. So here is an important subroutine. So given a flow and a path, we compute the bottleneck using as the smallest residual capacities in the residual graph. And then for every forward edge, we will increment the flow and redistribute on the flow on the backward edges. Um, and that's giving rise to a new, a new, better improved flow on this network. Okay, so we have to, well, let me now see that, is this actually now correct? So if we are computing in this way a new flow, call it f prime, the notation with prime may perhaps think about calculus, but we are very far away from derivatives, so I'm very far away from calculus. So f prime is what we will use for the new assignment of a flow on all the edges in the network. We have to say that it is a flow, which means that we do not exceed the capacities, and also we respect the conservation laws. Okay, um, we're only going to change the flow on the augmenting part, capital P. So it's only those edges that we have to consider. So we also have the bottleneck as the smallest residual capacity on the edges, so that will be important as well. So on an edge on this part, we have a forward edge. In a forward edge, we add the value of the bottleneck. Now, the bottleneck was the smallest residual capacity, so it is actually for every edge, it's bounded by the capacity minus the flow on it. So, and if you see, it works out very nice. We see that the new flow still respects the capacity of every forward edge. If we now look at the backward edge, well, actually here it's actually much simpler. We are subtracting positive numbers. So the bottleneck is always less than the flow on an edge. So again, it's the minimum residual capacity. It's also the minimum value of what we can redirect. So therefore, if we subtract, the f prime will actually be less than the capacity. Okay, so the capacity conditions on a flow on this function on the edges holds. What about the conservation conditions, which state that a flow has no leaks, so what comes in goes out? So we also have to show that on this new flow, for all the edges on the augmenting part, what comes in goes out. So we have forward edges. On forward edges, we compute what comes in. So we are applying this formula. When we apply the formula, we have that the sum of, so we apply the definition of the new flow. On a forward edge, we add the value of the bottleneck. We recognize in some sense it's the same definition here. We have the definition then applied to the original flow. Now, in the original flow, what we have is that the conservation conditions are respected. So then you see that, of course, we have what needs to be proven for the forward edges. The next exercise asks you to verify this for the backward edges. So here is this exercise. The purpose of this exercise is that you think again, what does it mean that we have a flow? How can we express the conservation conditions? And again, what happens with a backward edge? Okay, so then comes the Ford-Fulkerson algorithm. So the algorithms in this course are all, in some sense, very uh, terse, can be written very shortly. Although here there are a lot of subroutines there. The thing that I want to emphasize here is the while. So we start the chapter on iterative algorithms. So there is a while loop. And that's an indication that as long as there is a path in the residual graph, we will augment the flow. Now, when we have an algorithm, and actually the condition for an algorithm to be an algorithm is that it terminates. So for the remainder of this pre-recording, we will look at that question. Does this iterative algorithm terminate? Okay, so there will be a very extensive running example in the second half of this lecture in the next pre-recording. But let's illustrate some of the steps. So if we have found an augmenting path, so at the left in the dashed edges, you see the path from source to sink in the residual graph. And then we impose the flow. So we, on the forward edges, we add 10. On the backward edges, we subtract 10. So we have this simplest non-trivial example is good enough to illustrate all cases in the algorithm. So you see the bottleneck is 10, so I should have pointed that out. So 10, 10, 10, it's not that it's simple. So we have 10 everywhere, so the bottleneck is 10. We have a backward edge going from V to U, where we can actually redirect the flow of 10, and we are going to direct the flow, 10 of the flow from U to V. So at the right, so we then assign also the original flow is still there. So we started with 20, 20, but we have redistributed 10 to the from the edges U and V to U. Okay, so I hope it's obvious that this is the end of the algorithm. So you have the maximum flow of 30 in this algorithm. So if you now formulate the residual graph, so you see that you only have incoming edges into the source, so you cannot make a path from source to sink. So this ends the algorithm illustrated on this simplest non-trivial example. All right, is this algorithm now efficient? And first of all, does it terminate? Here is a first property. This is a course on discrete problems. So we will assume, and that was the case in the example as well, that all the capacities are integer values. What if they are not? Well, every rational number can approximate a real number arbitrarily close. You can always transform it into an integer value problem. That's the very short answer. Not too good, but we will see what the implications are of that. Okay, so if the input is integer, then it will actually stay integer. All the numbers will be integer. That's actually quite interesting and quite helpful for the termination. Okay, so let's prove this lemma by induction. Um, Induction on the stages in the algorithm. So we assume, first of all, the base case. We initialize the flow to 0. 0 is a very nice integer number. And then we assume that the algorithm starts from an integer flow. And we have to show that in the next stage, the new flow, what we called f prime, will also assign integer numbers to new integer numbers to the flow. Okay, when we construct the residual graph, we have the formula that's only subtracting integer numbers or assigning an integer number from the flow of the previous stage. So there is no way how actually non-integer numbers can arise. It's also very important that all the numbers, the capacities, are non-negative, and we preserve the capacity conditions in our flow, in our new flow. So we will never see negative numbers nowhere. The bottleneck is actually the smallest residual capacity. And that's also, if you take integers, you take the smallest integer, that will also lead to an integer that is non-negative. Then finally, in the formula for constructing flow on the augmented path, we are going to add the bottleneck, or we're going to subtract a number that is smallest than all the existing flows that there is already on the backward edges. So we have this verified in going from one stage to the other stage that on the new flow everything will remain integer. Integer capacities imply integer flows is the summary of this reasoning. Okay, so now it's important that the value of the bottleneck is never 0 because we have an augmenting path from source to sink. And in every stage, the flow actually increases by the value of the bottleneck. And that means that the new flow will be larger. So we have a strictly increasing flow. It's also important that in a directed graph we can have cycles, but we have no repeat nodes on our path. So we never visit the sink again. Okay, that's it, basically. We have integer values and the flow value always strictly increases. How does this help with the termination? Well, we have an upper bound on the maximum flow by the given integer values. And here is that upper bound. So we have the capital C, which is the sum of all the capacities. And that is the absolute upper bound. So that's really the maximum that you can get. typically it will be a lot less. So with the sum of the capacities, we have that the algorithm does at most C iterations, and therefore it terminates. Okay, let's go carefully through the proof, simply observing that since this is the sum of all the capacities, the value of the flow can never exceed that big C. Initially it is 0. So the previous lemma stated that the bottleneck is always positive if there is a path. As long as the algorithm runs, we will increase the flow by at least 1. Because the bottleneck, because everything is integer capacities imply integer flows. So the bottleneck is also an integer. And we start at 0 and we do not get higher than the capacity. Okay, an iterative algorithm, a proper algorithm, it terminates. Okay, when we talk about algorithms, we have to be, however, careful. We're not entirely there yet. We haven't spoken yet about the data structures. So if we would store our graph in a data structure that would require many um, steps, then that would not be efficient. So we will use the adjacency list representation. Here I illustrate on an example the adjacency list representation again. So we have an array of lists, as many elements in that array as we have vertices. And for every vertex, we list all the adjacent vertices. For a weighted graph, we also list the values, the capacities of the edges. So, and we store essentially this twice. We have the incoming and the outcoming edges. This has the advantage that if we flip orientation, and that's actually what we do in the residual graph, we are flipping edges. Flipping edges is extremely easy. You just change the roles of the first array of lists to the second array of lists. So that's a clear benefit of this adjacency list representation. The graphs we are working with are typically not dense, so the number of edges is typically proportional to the number of vertices. Okay, we have proven the termination. We have to show that it is still an efficient algorithm. Okay, here is the running time, and in the running time, I should indicate here that our graph is connected. So that's actually the main constraint. So what we actually have is that in a connected graph, we have a spanning tree, and a tree is characterized by n minus 1 edges. So it's probably I copied the assumption from the textbook, but our graphs are connected. So it means that we have a lower bound on the number of edges. Okay, so we then can show that the running time, we have C iterations, that big C is the sum of all costs. And what we have is we have the number of iterations. Now we have to show that the number of operations we do per step is bounded by the m, the number of edges. Well, we consider the residual graph. The residual graph has at most 2 times m edges. We may double the number of edges by adding the backward edges. It's also stored in an adjacency list representation. And we run the breadth first or the depth first search to find a path from source to sink. That's an algorithm that one of the earlier algorithms we considered, which is also considered in any data structures course. By the assumption, and actually I should simplify this, by the assumption we have that the number of edges is at least n minus 1 because the graph is connected. Therefore, we can bound that breadth first or depth first search by the number of edges. Okay, we look at a path, and that path is at most, there is no repeat node, so in a path we may visit all the intermediate nodes, so we have to go from source to sink. So when we visit all those edges, we do n minus 1 steps. That's again bounded, and actually it's bounded also by this big O of m. Okay, then what do? We compute the new flow. The construction of this new graph visits all the edges. So the total cost per step is bounded by the total number of edges. So our Ford-Fulkerson algorithm is a polynomial time algorithm. It is linear in the number of edges times the sum of the capacities. Okay, so that concludes. That's the first result. I will end with the notion of pseudo polynomial time. And in some sense, we could have made that comment already at the end of the last lecture on dynamic programming, where we also discretized a problem and where the sum of the weights was actually appearing in the bound. The Ford-Fulkerson algorithm is in some sense similar. Now, and I mentioned earlier the size of the real numbers, and that you can approximate this always with rational numbers. Now, of course, these rational numbers, they may grow in size. So the preciser you want your rational numbers, the higher the more decimal places you pick in your expansion of the real numbers, the longer the numbers are getting. So if you want an accuracy of 6 decimal places, you're going to have that your costs might be 1,000,000. So you may have to do 1,000,000 steps. So therefore, algorithms that are, we always express our algorithms in terms of the size of the input. If the size of the input is also depending on the size of the numbers, then actually we have the pseudo polynomial, because if we allow all integer numbers, essentially integer numbers, they can grow unboundedly as well. So algorithms are strongly polynomial if they are independent of the bit size. So there is the bit size complexity, which we don't really explicitly address in this course so far, but we have to be mindful of this, that the algorithm of Ford-Fulkerson is not, in the strict sense, a strongly polynomial algorithm. Okay, so this ends the first half of this lecture, where we introduce the Ford-Fulkerson algorithm. In the second half, we will start by running this on a more extensive example. So that will be the benefit of it if some things were not clear enough yet. And we will prove properties, also indicate how And you may have wondered already, the number of iterations, capital C, that's indeed a huge number sometimes. Can this be reached? And we will give an example where this is really the case and what we can do about this. We give a variation of the max flow algorithm.